We've just had a few lectures in a row that were pretty heavy on definitions and theorems and proofs, and then new algorithms, and then theorems and proofs about the new algorithms, and so I guess a breather is warranted. Okay, so I'm racking my brains trying to think of a fun breather topic. Oh right, there's one obvious choice. It's graphs. So why don't we spend this lecture talking some more about graphs? In fact, I have a bunch of small topics related to traversals that I've been saving up. I didn't want to talk about these during the lecture on DFS or the lecture on BFS because, as we'll see, many of the applications I'm going to discuss in this lecture can actually be solved with either DFS or BFS. So it made sense to talk about them, I guess, in neutral territory. The first one is actually a definition that, if you already knew about this, you might have thought that it was conspicuously absent from our very first lecture on graphs because it is something that tends to come up early and it's sort of important. And the reason I was saving it was that I wanted to wait until we knew about traversals before talking about it further. Okay, so it's a definition of something called a bipartite graph. If you have an undirected graph, we say that it is bipartite if you can find some way of dividing all of the vertices of the graph up between two sets, we'll call one of them x and one of them y, such that every edge of the graph passes between those two sets. So there's no requirement that any vertices have any particular edges attached to them, only that if there is some edge in the graph, it must cross over between x and y. So it would not be allowed, for example, to have an edge between two vertices in x or between two vertices in y. If you can find some way of dividing vertices like that, then we say that the graph is bipartite, and we say that the two sets that you came up with, x and y, constitute a bipartition. Now, I don't know, like a notational anecdote here. As far as I know, so way back when I learned about what a bipartite graph was in a graph theory course long ago, and maybe if you've seen bipartite graphs, you can corroborate this, but it appears as if every single person in history that has ever introduced the concept of a bipartite graph has drawn basically this diagram. These two sort of oval-shaped things with all the vertices inside of them, and then the edges crossing over between them. So there's something very important or powerful about this representation as far as visualizing the idea of a bipartite graph. And to this day, when I think about bipartite graphs, for some reason, this diagram comes to mind. But for our purposes, it's actually sort of useful to think of a bipartite graph a little bit differently. There's an equivalent definition that I think we'll find quite helpful given what we're about to do, which is that instead of trying to rearrange the vertices on the page to fall into two sets x and y, let's leave them where they are. Let's maintain a nice pretty drawing of the graph and instead color vertices with two colors. Okay, so here's a different graph. This is not the same graph that was on the previous slide, but notice how this diagram does look much more aesthetically pleasing. So an alternative definition of bipartite is what we would call two-colorable. So the idea here is that if I can find some way of coloring every vertex of my graph with one of two colors, such that it is never the case that an edge connects two vertices of the same color, so all edges go between, here I've used red and blue, so all edges go between red and blue, then I have what's called a two-coloring of the graph. And the two coloring really is just a bipartition. In other words, if I color my vertices red and blue such that every edge crosses from a red vertex to a blue vertex, all I really have to do is to define that every vertex that I colored blue is actually part of my set X, and every vertex that I colored red is part of my set Y. And you'll notice that the definition we gave a minute ago basically then applies perfectly. So it's a matter of personal taste how you choose to visualize it. I find that thinking about things in terms of two colorings tends to make it a bit easier to prove stuff because you can leave the graph where it is, you can draw the graph in an aesthetically pleasing way, and just decide about the colors of vertices. One thing I need to make pretty clear early on here is that I've decided to use red and blue as my colors, but notice that in the description I never mention the word red or the word blue. I just say two colors. And of course, obviously we could use any two colors we wanted, but more importantly, when we get down to talking about the specific color that a vertex receives, there really is no meaning behind one or the other of the two colors. That is, if I talk about the color of this vertex here, let's just clear this up. If I talk about the color of this vertex here? Well, yes, on the page it appears to be red. But ultimately, if you produce some two-coloring of this graph, then we could argue that whatever color you assign to this vertex is irrelevant. All we know is that each of the vertices of the graphs has been assigned a color, so I'm just going to choose to call whatever color you gave this vertex red. I can just give it that name. The names that I give to colors really makes no difference. The key is simply that if I look at any edge in the graph, if I'm talking about a two-coloring, if I look at any edge, it must connect a vertex of one color with a vertex of the other color. If we have this property, we've created what's called a two-coloring, which is equivalent to a bipartition. Although you'll notice that I guess I wrote the 2 as a numeral, so maybe we could ask the question, hey, if there is no two-coloring available, could we talk about maybe a 3-coloring? Or maybe a 4-coloring? And the answer is yes, although that wouldn't be equivalent to a bipartition. A bipartition is a two-coloring. Hold that thought, though. We're going to come back to the idea of coloring in graphs briefly in a very long time, something like 10 lectures from now. What I want to do now, though, is prove some properties of bipartite graphs. In particular, I actually want to use traversal algorithms as a way of asserting a pretty interesting and powerful link between cycles and the existence of bipartitions. Now, the first step towards doing that is to define another infinite family of graphs. And it's a pretty simple one. I'm going to define what are called the cycle graphs, and we denote them by Cn. And what I have drawn here is C5. So the cycle graph Cn is just a cycle on n vertices and nothing else. And if you think about it, you'll realize that a cycle on n vertices also has n edges. I have decided that cycles begin at n equals 3 because I can't think of a way with an undirected graph of creating a cycle on 2 vertices. There are those that would try and define Cn even for n equals 1. That is, they could argue that this single vertex is actually a cycle of length 1 or something. I don't want to think about that too much, so we won't worry about that. We will assume that our cycle graphs start with n equals 3. Now, I guess since we're taking a bit of a breather, this is a good opportunity to write some sort of unconventional proofs. And while I was making this particular set of slides, I realized there were certain styles of proof, completely valid styles, ones that people actually use all the time, that we don't get the chance to write too much in this course. And I figured, why not try doing that in this lecture when we're talking about bipartite graphs and two colorings? So let's start with this. I would like to prove that C4, the cycle on 4 vertices, is bipartite. Okay, so I'll show you my proof of that, and you can tell me whether you like it or not. Are you ready? All right, here it is. There you go. I have been able to produce a two-coloring. There it is. And I mentioned before that one of the reasons I love graphs so much is that when you write proofs on graphs, often you can incorporate nice-looking diagrams into your proofs. In this case, it turns out the theorem I was proving isn't really that powerful of a statement. I'm proving a property of one small graph, so actually maybe this shouldn't even be promoted to theorem. I'm not even sure if it counts as a lemma, but in any event, if I want to prove it, there it is. If I want to show that a graph is two-colorable, that a graph is bipartite, all I have to do is produce a bipartition. And then, of course, the graph has to be bipartite if at least one bipartition exists. So it's pretty easy to prove a positive, to prove that something does exist if you are able to find that thing. Now, we already know that there are plenty of ways of writing a proof that proves that something does exist, even if you can't actually find an example of it, but that tends to be more involved. Okay, so we now know that C4 is bipartite, and I swear I'm going somewhere with this. I want to prove something a little bit more difficult now, which is that C3, the cycle on 3 vertices, is not bipartite. This is an example of proving a negative, so it's not like I can find an example of something that demonstrates this property. Whereas to prove C4 is bipartite, I can just show you a two-coloring of C4. What do I do for C3 if it isn't bipartite? Okay, I have two options, and the slides are going to want to present them in the opposite order I do, and that's just too bad. I'll start with the sort of second option and sketch that out. But the option I'm going to go with is a style of proof that we quite rightfully don't often see, because it turns out that usually it's a huge amount of work and not really worth it. But I'll show it off in this case. But before I do that, I want to illustrate one way we could go about proving that C3 is not bipartite. We could say, let's consider what would happen if we tried to create a two-coloring of C3, of our cycle on 3 vertices. So under a two-coloring, every vertex must receive a color. Okay, so this vertex here must receive a color. Let's decide that the color it receives is red. Now, you could argue that if we're coloring with red and blue, doesn't that leave out an important case? What happens if its color is blue? As I mentioned earlier, the actual identities of our two colors are sort of irrelevant. Nowhere in any of the proofs I'm going to write later, for example, do I mention red and blue specifically. I just talk about the color of a vertex and the opposite color of that color. So we could argue that regardless of how you chose to color this vertex, just call whatever color you gave it red. So just declare that the name of that color is now red. Okay, so this vertex is red. Let's look at both of its neighbors. So we can see it has two edges incident to it, and that means it has two neighbors. And by the coloring property we're trying to achieve, by the properties that govern bipartitions, it must be the case, so I can't actually color it blue because my drawing program is rather primitive. Because of that, it must be the case that both of the two neighbors of my red vertex must be blue. There is no other choice. If this vertex is red, the other two vertices must be blue. And I realize now that I've gotten myself into trouble because if I look at this edge here, this far edge away from my starting point, it now connects two blue vertices. Now, we could write this up as a proof. With a couple of paragraphs, we could assert that although it looks as if I constructed my way into this mess, actually I had no choice. And that's a thought we should hold because when it comes time to discuss algorithms, I'm going to leverage that insight again. That once I've set the color of one vertex, a bunch of other vertices have their colors fixed. They're forced by that decision. And whether I chose red or blue for my initial vertex, ultimately I'm going to end up with this edge creating a contradiction. And if we wrote this up, as I said, maybe a couple of paragraphs, that would be sufficient to prove that C3 is not bipartite. But the proof I actually want to use, the canonical proof I'm going to show, is something different. What I'm going to demonstrate instead is that, well, okay, so I have three vertices, and I'm arguing that there is no way, so no matter, among all the different ways you could color these three vertices, none of them will meet the criteria to be a bipartition. Okay, how many ways to color them are there? Well, there are three vertices, and each vertex can receive one of two colors. So even if I'm not the least bit careful about which vertex receives which color, the number of possible colorings is just 2 to the 3, which is equal to 8. So if I want to argue that no coloring meets the criteria, one option, a sort of weird option, maybe an option of last resort, is just to try every possibility. If I show you all 8 colorings, and you can look at them and we can both agree that none of them are bipartitions, then that actually gives me my proof. This is called a proof by exhaustion. So in a case where you're proving something about a finite set of possible outcomes or possibilities, you could just show that on every single possibility, your statement either holds or does not hold, whatever it is you're trying to prove. It's a proof by exhaustion because you have enumerated all cases exhaustively, and because you're probably exhausted when you're done. So here is a proof by exhaustion that C3 is not two colorable. So I choose two colors, and I show off every possible way of assigning each of the vertices of C3 one of those two colors. And I observe that in all possible cases, you're going to have an edge that connects two vertices of the same color. So these ones here, I'm just crossing off cases where I see an edge connecting two red vertices. There we go. And in all of the remaining cases, I have an edge connecting two blue vertices. And so none of these colorings constitutes a bipartition. And this is a valid proof. Hopefully it's clear why we don't usually resort to this. It's generally a last resort. And there are plenty of cases actually where people sit down to write a proof, they realize they have no other options, but that maybe a proof by exhaustion would work, and then they just give up. Because sometimes the proof by exhaustion is so onerous that you'd rather have no proof and just keep brainstorming than try and actually work out a proof by exhaustion. Consider that this is a 3-vertex graph, and there were 8 distinct cases. If you tried to write the proof by exhaustion for, I don't know, like C10 or something, you'd probably understand why proofs by exhaustion are not very much fun. So that is an option, and it's good to know about, I don't know if it's an obscure technique, but lesser used proof techniques like that. There are some cases where you have to resort to unconventional methods to prove some mathematical statement. But let's hope we do not have to see a proof by exhaustion again in the near future. Okay, so I've just proven that C4 is bipartite and C3 isn't bipartite, using these weird sort of toy proofs that I think are really clever. But where am I actually going with this? What I actually want to prove is that cycles of even length if I have an even number of vertices in my cycle, those are always bipartite. And cycles of odd length, so let's say C3, C5, C7, those are never bipartite. And I'm going to use that information and then talk a bit about algorithms. And what we're going to end up realizing that whether or not a graph is bipartite simply depends on whether it contains certain types of cycles. Okay, here's the slides reminding me that I could also have proven this using the way I sketched out earlier. I could say, consider a case where I start coloring my graph and the first vertex has a certain color, and notice how the two remaining vertices must have the opposite color, and that results in a contradiction. Okay, the first theorem is, I'm going to prove that cycles of even length, so we can see here the theorem is saying that Cn is bipartite for all even integers n, which begins at 4, because there is no such thing as C2 in my reckoning. So if we consider there's C4, we can see there's a bipartition of it, there's C6, there's C8, and we can see that all of these are bipartite. I want to prove this is true for all cycles of even length. Okay, I'm going to do this by induction, and I could do it directly on n, so I could have n go up in steps of 2, so 4, 6, 8, 10. That would be completely valid, and there are those that could argue, probably pretty convincingly, that that would result in a pretty elegant proof. But for some reason, because of course, when one is writing a proof, there is the matter of personal taste, I am going to choose instead to use a different parameterization. And remember that just like back when we were solving recurrences and there were two different ways of doing it, if you're the person generating the mathematical thing, the proof or the derivation, then you do have the choice to use whichever method you're most comfortable with. And for some reason, I just like, when I have to use induction, when I write induction proofs using some induction variable that counts, I prefer it counting up in steps of 1. So if it were up to me, I would rather not worry about n going 2, 4, 6, 8. I would rather worry about some other variable k going 1, 2, 3, 4, or 2, 3, 4, 5. So I'm going to state the theorem in terms of a surrogate variable k, and I'm going to talk about C2k. So notice that if I think about Cn for an even integer n, there is a way of writing out n to be equal to 2k, because any even number can be written as 2 times k for some value of k. By framing the theorem this way, it allows me to write an induction proof where k just counts up in steps of 1. Now, to be honest, it isn't that bad. I mean, as I said, it's a valid form of proof to have n count up in steps of 2 for this. I don't think it would be that big of a deal for me to do that. The next theorem I want to prove, though, where I'm talking about odd numbers, I find it way easier to think about in terms of a secondary variable k. So I want to do both theorems using a sort of, I don't know, symmetric induction pattern. Okay, so I'm going to count up with k in steps of 1. So when k equals 2, then I'm talking about C4, C2k. When k equals 3, I'm talking about C6. So my proof is going to be by induction on k. Now, when k equals 2, I'm talking about C4. And my basis is easy because I can just say, hey, look at my coloring of C4. Therefore, C4 is bipartite. And that's my basis. Okay, good. So we already showed that off with a separate theorem anyway. My induction hypothesis is, suppose that C2k is bipartite for some k greater than or equal to 2. And what I intend to do is basically show that because C2k is bipartite, according to my hypothesis, that means I can consider some bipartition of it, some two-coloring of it. And once I have a two-coloring of C2k, I can just splice in a couple of extra vertices in a specific location, and all of a sudden I've got myself a copy of C2 times k plus 1. And I can show that it's pretty easy to show that this can be made to be bipartite too, that I can find a two-coloring of this. And that's going to give me my induction step. So I begin by assuming that C2k is bipartite for some value of k. And then the induction step is to construct a bipartition for the next value of k, so k plus 1. If I plug that in, I actually get C2k plus 2, or 2k all plus 2. Okay, so by the induction hypothesis, there does exist a two-coloring of C2k. This diagram is here for our convenience, but actually the entire proof is contained in text. So there are graph-theoretic proofs that do rely heavily on diagrams. This actually isn't one of them. The diagrams are mostly here just so that I've got something to draw all over while I'm talking about it. So by the induction hypothesis, there exists some two-coloring of C2k. For the sake of the diagram, just number the vertices according to a clockwise traversal of the cycle. So we'll say this is V1, and then we wrap all the way around, and the last vertex of C2k would be V2k. Notice that in my diagram, I have decided that V1 is colored red. Now, you have to be very careful with this sort of thing. So as I said, the proof itself is found only in the text in this case. This diagram is just a way of illustrating the steps of the proof. It's a bit dangerous, though, if this diagram were part of the proof, to just go and assume that V1 got the color red, because somebody could look at it and say, hey, does the proof still work? Does the theorem still hold if V1 ends up being blue? If that's a worry, what you could do in your proof is add a line that says, define whatever color V1 has to be the color red, and define the other color to be called blue. Remember that we don't actually know anything about which colors were chosen, we just know a two coloring exists. It's up to me to decide how to interpret each of the colors. I know that V1 had to have some color, let's just assume that color's name is red. Okay, so what I'm going to do is I'm going to add two new vertices. I'm basically going to cut out the edge between V2K and V1, observing that in this two coloring that I have, V2K and V1 have to have opposite colors. So if I've defined V1 to be red, V2K has to be blue. So I get rid of the edge between them, and then I just splice in two new vertices. Okay, so the proof is trying to be magnanimous about what colors are. Notice that it doesn't say anything about red or blue. It just says that certain vertices take the opposite color of certain other vertices. In that way, the proof is getting away from this concern about deciding that a vertex is red or a vertex is blue or whatever. So I add these two extra vertices, and I say V2K plus 1, that would be this vertex here, takes the opposite color of V2K. And then V2K plus 2, which would be this vertex here, takes the opposite color of V1. Now, by asserting this, basically what I'm saying is that, of course, what I want when I'm done is a two coloring of this, C2K all plus 2. And so I'm trying to define the colors in a way that forces that to be the case. If V2K plus 1 has the opposite color of V2K, well, then the two coloring is preserved for these two vertices. If V2K plus 2 has the opposite color of V1, then, of course, this edge here obeys the two coloring. And actually, sort of between the lines, we can assert that these two vertices have to have opposite colors. Because as I said earlier, V2K and V1 have opposite colors of each other. And by sort of interleaving, like making these two things have the same color and these two things have the same color, I'm sort of forcing this edge to connect two things of different colors. If I look at what I end up with, though, I observe that the only thing I really changed was this little segment here. The only modifications I made that could have broken the two coloring are inside this box. And I was able to define those modifications in a way that makes it clear that I still have a two coloring of my resulting new graph. Additionally, I started with a two coloring of C2K. So if I go all the way around the cycle, all the vertices, I guess, below this line, that two coloring is still fine. I didn't change anything about it. I didn't add or remove any edges down there. So it makes sense if that was a two coloring to begin with, it's still a two coloring now. So because V2K and V1 had opposite colors in the original two coloring, and I spliced these vertices in and I set their colors according to carefully chosen rules, the resulting graph is a two coloring of C2K plus 2. The text of the proof isn't saying, I guess, as clearly the thing I just said, so it doesn't really need to point that out, but just so we know, remember that there is this entire rest of the cycle it's not pictured on the slide, that is already two colored. So we started with a valid two coloring of the rest of C2K, and we changed nothing, and so that remains a valid two coloring of the rest of C2K. In any event, I've been able to produce a two coloring of C2K plus 2, and that's what I need for the induction step. And therefore, C2K plus 2 is bipartite, and by induction, all cycles of even length are bipartite. So C2K is bipartite for all k greater than or equal to 2. Okay, so that's the case of even cycles. Every even cycle is bipartite. What about odd cycles? We already know that there's at least one odd cycle that isn't bipartite. It turns out that no odd cycles are bipartite. So I cannot find a two coloring of C3, I cannot find a two coloring of C5 or C7 or any other cycle of odd length. And so I've stated this theorem in similar terms to the previous one. So this theorem is equivalent to the statement that Cn is not bipartite for all odd integers n greater than or equal to 3. But for the sake of making my proof easier for me to write, it's a matter of personal taste, I would rather use a surrogate variable k and talk about C2k plus 1. If you have any odd integer n, you can write it in the form of 2k plus 1 for some value of k. It'll always be an even number plus 1. And so I'm choosing to do that because then I can have k count up in steps of 1 as before. This is also going to be by induction. In fact, the framework of the proof is pretty much the same as the framework of the previous proof, with, of course, the key difference being the inversion of the existence of a bipartition. That is, in this case, there is no bipartition. The induction step contains a sort of weird trick, and I was really pleased when I came up with this idea because I can't recall having used this trick anywhere else in this course. What I'm going to do is actually have the induction step involve a contradiction. So I'm going to have my hypothesis say, suppose that we know, let's say, that C3 is not bipartite. Then in the induction step, I'll say, suppose that C5 is bipartite. And I will show that if C5 is bipartite, I can create a bipartition of C3, which will be a contradiction because our hypothesis says the opposite of that. And that's going to be enough to give me my induction step. Okay, so the proof is by induction on K. Now, when K equals 1, if I look at C2K plus 1, I'm actually talking about C3. And in this case, I don't know if I want to assert the basis independently because then I have to show all 8 of these again. So I could just say, look, we already proved that. There was a theorem we gave earlier with our proof by exhaustion that showed that C3 is not bipartite. So in any event, we know that C3 is not bipartite, so we have a basis. And then our hypothesis is, suppose that C2K plus 1 is not bipartite for some value of K greater than or equal to 1. And what I'm going to do in my induction step is almost the reverse of what I did in the induction step for the previous theorem. So in the previous theorem, I took the coloring that I knew existed, the 2 coloring of C2K, and expanded it to create a copy of C2K plus 2. Here what I'm going to do is, suppose there is a bipartition of C2K plus 3. If I want to consider the case K plus 1 in my induction step, I have to consider C of 2 and then plug K plus 1 in there, which ends up being C2K plus 3. I'm going to suppose that there is a bipartition of this. And notice, just like we usually do with contradiction proofs, we want to make a note of this assumption. So I'm making an assumption here. I'm inside the induction step. Now, inside the induction step, we hold that the hypothesis is true. So that is, eagle-eyed viewers will notice that I do say suppose in my induction hypothesis, but the induction hypothesis is considered to be, it is accepted as true in the induction step. And so if we run into a contradiction inside this induction step as a result of one of these assumptions, this is the one that we're going to blame because this is the assumption we made most recently and the one that is the most tenuous. So in the induction step, I make this assumption. Suppose that there is a bipartition of C2K plus 3. The goal of my induction step here is to show that no bipartition of C2K plus 3 exists. That is the theorem I am trying to prove. So I'm going to suppose that one does exist, and then I'm going to drive towards a contradiction. The contradiction I'm going to come up with is to show that if there is a bipartition of C2K plus 3, and I can pretty much spoil how I'm going to do that now, I'm just going to say, in that case, if I clip out these 2 vertices, I can produce a bipartition of C2K plus 1. But by the hypothesis, there is no bipartition of C2K plus 1, and that's a contradiction. And so that's what I intend to do here. I think that's pretty cool because we don't usually get a chance to combine proof by contradiction and proof by induction. I think the core of this is a proof by contradiction, but it still relies on the structure, the scaffolding of the proof by induction to be able to, move forward in an orderly manner. Okay, so suppose that there is a bipartition of C2K plus 3. And as before, let's number the vertices. For the sake of our diagram, number the vertices according to a clockwise traversal. So they're numbered going around the cycle. So what do we know about such a bipartition? Okay, well, we know that if we look at the vertices nearby to V1, we've got V2K plus 1, and we've got V2K plus 3, which is sort of 2 over from V2K plus 1, and they must have the same color. So why do I know that? Well, I know that both of them are attached to this vertex here. So notice how, again, the proof doesn't talk about red or blue. We're trying to avoid identifying specific colors. I mean, we can choose in our diagram to draw red or blue for the sake of our visual convenience, but ultimately all we know is that the color of V2K plus 2 is the opposite color of its 2 neighbors. And that means, of course, there being only 2 colors, the 2 neighbors of V2K plus 2 must have the same color as each other. Okay, and then similarly, this vertex and this vertex, V2K plus 2 and V1, must have the same color as each other. So we have these sort of 2 groups that each have the same color as each other and the opposite color of the other group. So what that tells us, of course, is that V2K plus 1 must be the opposite color of V1. If you put all of those insights together, V2K plus 1 and V1 must have the opposite color. Why is that important? Well, it's important because that means if I add this edge, that my two coloring doesn't get broken because they have the opposite color. Adding a new edge between two vertices with opposite colors doesn't break anything. If I do that and then I go and delete some vertices, and if you think about it, deleting vertices and edges can't break the two coloring either, then what I'm left over with is a copy of C2K plus 1. And it's also a two-colored copy of it because I started with a two coloring of C2K plus 3, and of course, as before, there is an entire cycle down here that remains correctly two-colored. I haven't changed the colors of any vertices. I started with a two coloring of C2K plus 3, and I was able to prune away a couple of vertices and create a two coloring of C2K plus 1. So I do that, and now I have this copy of C2K plus 1, and it is a bipartition. It is a two coloring of C2K plus 1. Now the problem with that is that by the induction hypothesis, no such thing exists. So this is a contradiction. Okay, so let's trace backwards and figure out who to blame for it. So we go back and notice that we made this assumption here. In the induction step, we accept the hypothesis as true, because certainly it's true that although we use the word suppose here, we do have evidence that the hypothesis holds, at least in some cases. That's part of the bootstrapping process of writing an induction proof. Versus this is just a fantasy of ours. Suppose that a bipartition exists. We have no evidence that such a thing exists. So this was the most recent assumption we made and the most tenuous one, and it's the only one inside the induction step. And what I observed was, based on this assumption, if I suppose that such a bipartition exists, and then I follow that logic through, I end up with a contradiction. That means that if this is true, a contradiction ensues, which means in turn that this is impossible. Therefore, no bipartition of C2K plus 3 exists. And that's what I wanted to prove in the induction step. Therefore, the theorem holds for K plus 1. And since I was able to establish the induction step, that means I can now say by induction, C2K plus 1 is not bipartite for all K greater than or equal to 1. Okay, so an exercise, a follow-up exercise. This is a really important proof in and of itself, although the reason it's a relatively mild exercise is just that we've already actually provided most of the detail of it. All we have to do is cross the finish line here, which is prove that any graph which contains a cycle of odd length is not bipartite. Notice that all I've actually proven just now was that if I look at a graph which is just a cycle and nothing else, that is not bipartite. But what about the example where I've got a graph full of all sorts of other vertices that happens to contain a copy of C5 buried in it somewhere? It sort of follows that that shouldn't be bipartite, but we should go and prove that. Let's just make this graph even bigger. We'll link all of these cycles together. There we go. So the question is, can we prove if a graph contains a copy of, let's say, C5 or C3 buried in it somewhere, that graph cannot ever be bipartite? And the way you'd prove this, I guess, the way I would suggest doing it is, suppose a bipartition exists, and then strip away the rest of the graph, the part that isn't the odd cycle that you care about, and just look at that odd, I'm making a real mess of this, but look at that odd cycle and argue that clearly that can't be a bipartition of the odd cycle. Now, there is actually a sort of complementary result that I want to prove, a really powerful one, and I'll spoil it. It turns out that any graph which does not contain a cycle of odd length is bipartite. In other words, the only thing preventing a graph from being bipartite is the existence of a cycle of odd length. Now, that is not this proof here. This proof is sort of the other side of that coin. Before I get to that result, which I think is really powerful for tons of different reasons, I want to talk about algorithms, because it turns out that's actually a result we can prove with the aid of an algorithm. Okay, so our task is design an algorithm which takes a connected, since when are we talking about connected? Design an algorithm which takes a connected undirected graph and decides whether or not it is bipartite. And if it is bipartite, find a bipartition. And I'll tell you in advance, the way I'm going to approach this is I'm going to design an algorithm to find bipartitions and then show that if what it comes up with is a valid bipartition, the graph must be bipartite, obviously. And if it isn't a valid bipartition, then the graph cannot be bipartite. I have to explain why I said connected graph, though. So why am I talking about just connected graphs? I didn't add that restriction before. So whether or not a graph is connected, it could still be bipartite. The reason I only want to focus on connected graphs here is just for convenience. So what we can observe is, if we look at this big graph here, which has 5 connected components, this graph may or may not be bipartite, although actually my money is on no. But whether it's bipartite or not can be decided by looking at each of the components independently. So because there is no edge connecting these two components here, then really if the whole graph is bipartite, that'll be because this is bipartite and separately, independently, this other component is also bipartite. So a disconnected graph is bipartite if each of its components is bipartite and each component can sort of be tested separately. What that means for us is that if we want to find bipartitions, or test if graphs are bipartite, we can focus on single connected components, on a connected graph. And if you ever want to ask the question about a disconnected graph, just break it up into connected components and then run our algorithm on each component separately. Okay, but how do we break up a graph into connected components? Okay, well, we're actually going to talk about that in a future lecture. For now, it suffices, I guess, to understand that there clearly is a way of doing that. Clearly, we can view a graph as an independent collection of connected components and then decide independently whether each component is bipartite or not. Okay, so what about finding a bipartition of a connected graph? So one huge observation, one that I foreshadowed earlier, is that if I pick some vertex, let's say I pick vertex A, and I assign it a color. Suppose I decide that vertex A must be blue. If vertex A is blue, automatically the three neighbors of vertex A are forced to be red. They have no other choice because, of course, there's only two colors available, and if vertex B ended up being blue, we would already have broken our two coloring. Okay, so vertex A is blue, which means vertices B, O, and R are red. But actually, now that I've set the colors of vertices B, O, and R, that means that vertex C, for example, as a neighbor of two red vertices, must be blue. And vertex N also must be blue, and then in turn vertex M must be red. And I realize after a while that actually inside this connected graph, once I set the color of any vertex, I sort of begin this chain reaction. A bunch of dominoes begin to fall. In fact, it looks as if as soon as I've set the color of A, the colors of every other vertex in the graph are forced based on the color I chose for A. So the neighbors of A become red, the neighbors of those things become blue, the neighbors of those things become red, and all the way down. In that sense, if I really buy into this logic of the chain reaction, if I want an algorithm to create the bipartition, the algorithm doesn't really have to do anything as far as decision making. All it has to do is let those dominoes fall. All I really want is an algorithm that takes my starting color and then propagates colors all the way around the graph. It propagates the colors to every vertex reachable from vertex A. And I realize that what I'm really talking about is just a graph traversal algorithm. So here's an idea. Start by setting the color of any vertex to blue, or whatever. You can use red if you want. Just choose a color for some arbitrary vertex. Then run a traversal starting at that vertex. It doesn't matter if it's DFS or BFS. All we care about is reaching all of the vertices that are reachable from the starting point. We don't care about the structure of the resulting traversal tree. I happen to have used BFS. Full disclosure, I did use BFS for this traversal tree here. The reason I like using BFS when I make slides is because since BFS trees are wider and shallower, they fit very well with my much wider and shallower slide format. That's pretty much it. I could have used DFS, and likely in practice, if I were to implement this, I likely would actually write it with DFS. So run a traversal starting at our starting point, fix the color of that vertex, and then as you visit each other vertex, so as I discover vertex B from vertex A, just set the color of the new vertex you discover to be the opposite color of its parent. So B becomes red. When I visit vertex C from B, C becomes blue. And then when I visit vertex D from C, D becomes red, and so on. Now, this is the best way, I think, for me to think of this. Like when I think of how I would perform this, how I would write code to do this, I think about it in terms of where would I write the assignment statements? Like where do I assign colors? Well, you assign the color of a vertex when you discover that vertex during the traversal. But there's an alternate way of thinking about it that's equivalent, isn't as operational. I guess it isn't the kind of thing you could turn into an algorithm as easily or would require more steps. But on the other hand, is it an easier way to view it in terms of the proof I'm going to provide as an exercise in a minute, which is alternatively, instead of saying, okay, whenever you reach a vertex, set its color to the opposite color of its parent, we could view that operation as generate the entire traversal tree, like before doing anything else. So before assigning any colors, generate the traversal tree, then set all of the vertices which appear on even numbered levels of the traversal tree to be blue, and set all of the vertices that appear on odd numbered levels to be red. Observe that if we do this, it is exactly the same. We end up with exactly the same effect as the description on the previous slide, because every vertex gets the opposite color of its parent, according to our previous idea. And if we color everything on alternating levels the same color, so all odd-numbered levels are red and all even-numbered levels are blue, then clearly every vertex has the opposite color of its parent and the opposite color of its children. So this is actually an equivalent way of saying the same thing. I have found, and this is a hint that you can choose to take or not, but I have found that thinking about this in terms of the levels of the tree makes this next exercise, this proof that I'm going to suggest, a lot easier to understand. It's easier to think of it as a concrete thing when we're counting, let's say, lengths of cycles. Okay, so what I've proposed is that we start at some arbitrary starting point and go around coloring the graph because certain colors get forced. Now, that doesn't mean the graph is necessarily bipartite, because I could go around coloring vertices of any graph I want, even a graph that clearly isn't bipartite, like C3. I mean, you can run a graph traversal on C3, and it would produce a coloring that doesn't make any sense. So I guess what it would do, let's try and draw a neater copy of C3 here. If I have a copy of C3 and I begin a traversal here, well, according to my logic, the first vertex gets colored blue, and then my traversal tree contains these two edges. And that means these two vertices automatically, by my logic, get colored red. Notice that, of course, I don't have a bipartition. Within the tree, I have a bipartition if I only consider tree edges, because since I defined the tree a certain way, it's actually guaranteed that every tree edge connects a red vertex to a blue vertex. If I look at this edge here, though, this cross edge, notice that, of course, it connects two red vertices together. And that means the graph, well, that means that what I've produced isn't a bipartition. So here's the question. Is this coloring process, when it fails, is it failing because it's bad at its job? Is it failing because there is a bipartition but it's just not finding it? Or is it failing because there is no bipartition? I intend to prove that it's the second thing, that if the graph is bipartite, this coloring process will always produce a bipartition. It's not just going to be lucky sometimes and unlucky at other times. So that's where we have to go with this. It isn't, what I was able to define just now with trees and levels only said that there's a way of coloring the tree. It didn't guarantee that the coloring I come up with will always be a bipartition. Okay, so I color the vertices of the graph starting from some arbitrary starting point, either according to the level of the tree in which they appear or just with a simple parent-child relationship. Those turn out to be an equivalent way of phrasing the same operation. And now, of course, if it turns out that the coloring I produced is a bipartition, well, lucky me. In that case, the graph is obviously bipartite. So that's the easy case. If it happened that this particular red-blue assignment gave me a bipartition, then it's my lucky day. The question is it true that if what I come up with isn't a bipartition, that the graph is actually not bipartite, versus that I've simply done a bad job of creating a bipartition? So this particular graph here actually is bipartite. It turns out that this is a bipartition. But suppose I had something like this. So suppose there were this edge in the graph all along, and then I produced this coloring. Well, clearly this coloring is not a bipartition, because, you know, there are two red vertices next to each other along an edge. The question is, can I show that the only way this will ever happen is if the graph itself is not bipartite, and therefore use this property, the fact that what I came up with isn't a bipartition, as a way of saying, sorry, the graph is simply not bipartite? And the answer, it turns out, is yes. And for whatever reason, after teasing this for several slides, I'm going to make you write that proof. So prove that if I color things this way, so if I start and I color things where every vertex receives the opposite color as its parent in my traversal tree. If I end up with a non-tree edge that is incident to two vertices of the same color, so here I've invented a non-tree edge. And I need to make it very clear that this non-tree edge is for visualization purposes only. That is, the graph I was working with doesn't actually have an edge between G and L. I just made that up for the sake of the visualization. So suppose there's a non-tree edge that connects two vertices of the same color once I'm done my coloring process. The exercises prove that if that happens, the graph must contain a cycle of odd length. And this is actually a very profound result. Before I get to that, I want to explain, using my visualization, what I mean by that. So notice that, like I said a minute ago, the tree edges are always going to conform to a two coloring. It doesn't matter whether the graph is bipartite or not. Because of the way I've defined the tree, it is guaranteed that every tree edge connects a red vertex to a blue vertex, because you'll observe that every tree edge goes between an odd-numbered level and an even-numbered level. Either it starts at an odd-numbered level or it starts at an even-numbered level, but it always crosses between from odd to even. And therefore, because everything at odd-numbered levels has an opposite color from everything at even-numbered levels, every tree edge is guaranteed to connect two vertices of different colors. Okay, what I mean by that is that the only time you can break your coloring is with a non-tree edge. So if any non-tree edge happens to connect two vertices of the same color, then the graph must contain a cycle of odd length. I will observe that for this non-tree edge, that is definitely true. If I walk all the way around this cycle here, and then back across my non-tree edge, I will discover that I have walked around a cycle of odd length. Let's see, 1, 2, 3, 4, 5, 6, 7. Okay, there's a cycle of length 7. That's an odd length cycle. We know from earlier that no cycle of odd length is bipartite, and that no graph containing a cycle of odd length is bipartite, and therefore this graph is not bipartite. So if the coloring was bad, it's because no coloring exists. The particular non-tree edge I've drawn in here is just one case of many. This proof will apply to any non-tree edge that links two vertices of the same color. So it could be GL, it could be something like this one. Although this non-tree edge would never occur if I used BFS, because BFS trees have certain constraints. This might occur, I guess, in DFS. And DFS would be a valid traversal to use for this algorithm. I can end up with something like that. I can end up with something like, I don't know, this. Any example of a non-tree edge that connects two vertices of the same color implies the existence of a cycle of odd length. Now, I can give you a hint as to how you know where the cycle is. If I look at the non-tree edge and I look at the two vertices that it connects, there's going to be somewhere in the tree where those vertices have a common ancestor. We typically call that the lowest common ancestor. In this case, it's B. And you'll notice if I walk from G all the way up to B, and then from B back down to L, and then I cross the bridge, I will have encountered a cycle. The point of this proof is to prove that that cycle you end up with must be a cycle of odd length. Because, of course, you can, if we were to consider like a non-tree edge like G to M or something, well, there's a cycle there as well. If this non-tree edge exists, in fact, in general, if there's any non-tree edge, you can expect that the graph contains a cycle, because we know that our traversal tree is a tree. So if the graph contains any edge not in the tree, then if I add that edge to the tree, I'm guaranteed to create a cycle. That's the property we know about trees. So there's always going to be cycles created by non-tree edges. The point of this proof is to show that the particular cycle created by a non-tree edge between two vertices of the same color must always have odd length. And I've already given the hint that maybe interpreting the coloring as being based on the parity of level numbers, so odd levels are red, even levels are blue, might make that a little bit easier to prove. Once you have that proof, then it's pretty easy to cross the finish line for this incredibly important and powerful result, which is that any graph that contains no odd cycles is always bipartite. The only thing standing in the way from a graph being bipartite in all cases is the existence of an odd length cycle. And that's actually pretty incredible. If you think back to our definition of what bipartite meant, or what two colorings were, none of that really implied anything about odd length cycles, and yet it turns out it all comes down to odd length cycles. What's great about this characterization is that it actually allows us to state blanket results about whether graphs are bipartite based on their cycle structure. So, for example, before we knew about this result, if I were to say something like, hey, here's a free tree. So I'll just draw in a somewhat complicated free tree here. Here's a free tree. Could you tell me whether this free tree is bipartite? Well, you could stare at it for a minute and try coloring it in, and it turns out it is. But this result here, once we have this proof, this shows that all trees are bipartite, always, in all cases, because trees do not contain cycles, and therefore trees do not contain odd cycles. And so by having a result phrased in these terms, we can actually apply we have this blanket application to say all trees are bipartite automatically. No need for extra proofs, no need for extra algorithms, all trees are bipartite. And so this is a huge result. And we'll see bipartite graphs once or twice more in this course. They often come up in graph theory contexts. I don't know that we need them for quite a while, though. One thing, though, that I'll point out, we've managed managed also to do a sort of tour of interesting styles of proof. And this last proof here, so this proof plays in heavily to this proof. And once you have the exercise on this slide, it's pretty easy to get all the way here. What's interesting about this proof, though, is this proof is based on an algorithm. And if you use this proof to produce this proof, then what you've done is proven that graphs that do not have odd cycles are bipartite using an algorithm. We've actually managed to use an algorithm, a traversal algorithm, as a vehicle for one of our proofs. And I think that helps to cap off our sequence of unusual proofs. And now what I want to do is talk about a bunch of other applications of traversals. As I said at the beginning, I've been saving up a bunch of applications of traversals because it didn't feel right to talk about some of these applications in the DFS lecture or in the BFS lecture because I wanted to talk about them in neutral territory. The first one comes out of image processing. So consider this image. It is a very low resolution image for the sake of easy visualization. And suppose that I open my image editor and I would like to use the bucket fill tool. I decide that I want to change the color of this inner region of the heart to some other color. So I get my bucket fill tool, there it is. Actually, we shouldn't say bucket fill tool, we should say flood fill. That is the formal name of this operation. Anyway, I get my bucket fill tool out and I choose a new color and I click, let's say right here. And I'm sure you've used an image editor before, and you know that when you click with your bucket fill tool, what happens is the entire contiguous region of the image gets changed to a new color. So in other words, if I treat this image as a bunch of contiguous regions, the regions themselves could have an unusual shape. In this case, this region is mostly one large chunk, but it does have some concavities. And I set the entire region to a new color. If I were to use the bucket fill tool with a starting point, let's say inside the black border, it would fill in the entire border going all the way around. All of the pixels in this contiguous border would be filled in with a new color. The reason I want to illustrate that is to make it clear that the bucket fill operation may require, tracing all over the place and having to wrap around corners and following strange, unusual shapes that occur in the image. It turns out, though, that the flood fill operation fundamentally is a graph algorithm. Now, whether you choose to implement it with that consciously in mind or not, that's basically what it is. And every flood fill operation you're likely to have used deep down is probably either DFS or BFS. So we can model this operation in terms of a graph, and I'm going to start by describing the modeling, but I want to make it clear that we don't actually have to create the graph objects in memory. We could simply view the graph as existing implicitly. So I'll call this a pixel graph. So let's consider the entire set of pixels of this low resolution image. So we create a vertex for every pixel. And I'm going to try drawing this on the slide, but I know that the resolution, that it's going to be pretty small. So there's an example on the next slide about this. Basically, I make a vertex for every single pixel. So a vertex corresponds to every single position of a pixel in the image. And then I connect two vertices together by an edge if they are next to each other, so they're adjacent to each other in the image, and they have the same color. So all the vertices in this little lattice of black pixels get connected together, and all the vertices next to them in the pink region get connected together, but I never connect across the boundary between the pink region and the black region. And what we realize once we're done, so I'll show the result here. So, you can pause and zoom in on this to take a look at what's going on. What I have now are a sequence of components where each component consists of a contiguous region. I never have any connections between the pink region and the black region. But within the black region, I realize that if I start anywhere in the black region, like here, there is some path that takes me to every other pixel in the black region. So this contiguous region of black pixels is a connected component of the graph. There actually are also these regions of white pixels that are not contiguous with each other. In other words, if I do a flood fill over here, I'm only going to fill this portion because although there are other regions of white pixels, this is the contiguous region attached to my starting point. And if you look at the pixel graph, that property holds with the components of the graph as well. The connected component containing these pixels is distinct from the one containing these pixels over here because they are separate regions. So I can view my image as a graph where each of the vertices of the graph has degree at most 4. It could be connected to none of its neighbors, but it's connected to at most 4 of its neighbors, the one above, the one below, the one to the left, the one to the right. If I then want to perform the flood fill operation, all I do is find the pixel corresponding to my starting point. Let's say it's there. I perform a traversal that visits all of the vertices in that component, all of the pixels that have the same color in the same contiguous region, and I change their color. I could use either DFS or BFS. It doesn't really make any difference. All I want to do is visit all of those vertices. Okay, I skipped over a slide a minute ago. I want to make it clear, though, that it's true that I could represent this by actually creating a graph from the image. Like I could go create vertex objects for every single pixel. That would be fine, and it wouldn't really change much in terms of the running time. So the running time of DFS and BFS, as we know, is big theta of number of vertices plus number of edges. And if I wanted to physically create an adjacency list for my pixel graph, well, the space complexity of the adjacency list is also the number of vertices plus the number of edges. And creating the adjacency list would also take linear time. So if I wanted to create it, it wouldn't actually add anything asymptotically to the running time. But even so, it's worth noting, I don't actually have to create the physical graph objects because I don't need to make a list of neighbors for every vertex explicitly and store it in memory. Since what I could do instead is view the image as already being a graph. So that is, treat every pixel like it's a vertex to begin with. Don't create a separate vertex object, just treat a particular set of coordinates in the image like it's a vertex. I could write a function, for example, to return the neighbors of a particular vertex. What that function would do, so I'll draw, I don't know, I'll make a larger version of a diagram. If I say, give me the neighbors of the vertex corresponding to this pixel, I can write a function that just looks at all of the adjacent pixels and then returns a list of which pixels have the same color as the one that I started with. So I don't actually need to physically create in memory an adjacency list. I could view the image as a graph implicitly and therefore save a bit of space and a bit of time. And it wouldn't make any asymptotic difference either way. But in this and each of the coming applications, I want to make it clear that in some cases the graph modeling only has to exist in our heads. It only has to exist as a way of viewing the problem, not necessarily an explicit construction. And therefore, it doesn't cost anything extra for us to do that. And in fact, it can often save us tons of time because if I can find a way of modeling my problem with graphs, in this case, I was able to solve it then using a standard graph traversal algorithm, like right off the shelf, which means if I can model my problem as a graph, I can take down DFS or BFS from the shelf and not have to worry about analyzing it or understanding its complexity in any other way because I know already how fast DFS and BFS are and how they work. I know, for example, that they are guaranteed to visit every single vertex in the component. So by using one of these off-the-shelf algorithms, I save myself a lot of time proving correctness and proving efficiency. Okay, there's one application. How about this one? This one is much more obviously, I think, a graph application. So suppose I have a roadmap, and in this case, this is my starting point. I am there. Let's say I'm driving, and I want to end up here. Now, this is a very small version of this pathfinding problem, but we can come up with variants of this that span thousands of kilometers if we want to. What I want, given my starting point and my end point, I want to use some app on my phone to give me driving directions and give me a driving path between my start point and end point. And the question here is, first, what information that I have in this situation is actually useful to me? And it's pretty clear that most of the information on a map is actually useless. I'm driving, which means I can only be on the road. I don't care what's happening between roads. I'm not going to drive into a building. I don't care about the footpaths in front of a building. I don't care about the names of the buildings. I don't care about the structure of the harbor or anything else. I just care about which sequence of turns do I make. And that by itself is a good argument to try and model this with something like a graph. Because we saw, for example, with the bridges of Königsberg, that one of the big insights of that modeling was throwing away a bunch of irrelevant information. The next thing to think about is, okay, so of the information that I need, which I guess is just the structure of roads, how can that be modeled as a graph? And I guess my insight, what I think about is, suppose that I am already driving in this direction on this segment of road. Well, only one of two things is going to happen as far as I'm concerned. Either I get all the way to this intersection here, or I arrive at my destination somewhere in the middle. So unless I'm already imminently approaching my destination, once I'm already on a piece of road, I'm going to drive all the way along it until the next intersection. And that at the intersection, I might make a decision to turn or to keep going straight. So to me, it sounds like where I make decisions are intersections, and the roads themselves are pretty much just connections between intersections. And given that in graphs we tend to have a vertex-centric view of the world, and that if I think of a graph traversal, the decisions are made at vertices, it makes some sense to model the intersections as vertices. Okay, so I create a vertex for every road intersection, and that's a location where some routing decision must be made. And then I connect intersections together by edges, as long as they are connected by a segment of road. So these two vertices here get connected by this edge because there is actually a road between these two intersections. Okay, so now if I want driving directions, well, our pathfinding algorithms in graphs, so we already know how to find paths in a graph with DFS or BFS, our pathfinding algorithms work from vertex to vertex. And I only have defined intersections to be vertices, which means if I want to find a path from an arbitrary location along a road to another arbitrary location also along a road, I guess I need to find the nearest intersection. And I don't think that's very difficult. In this version of the problem, it looks like that is a pretty big leap. That is, if I say, for example, look, I'm going to get directions from this intersection to this intersection because those are the nearest intersections to my start and end points. It does look as if the process of finding the nearest intersection does do a lot of the work. But remember that it's likely if I'm parked along a road somewhere, the nearest intersection is a few hundred meters away at most, versus my actual destination could be far away. I could be planning a road trip from downtown Victoria to Toronto. And so having to find the nearest intersection, which might be a few hundred meters away along a road, isn't really that big of a deal. Most of the routing is happening in between. There's a question also, if I use intersections as vertices, what happens if I have a dead-end road? So what if there were a road that ran inland here and then just stopped? What I would do there is model it by a vertex of degree 1. So the decision you make at this intersection is you have to turn around, pretty much. But I could model dead-end roads if I needed to. So my modeling works fine, even if roads don't necessarily run all the way through. Okay, so to find a path between two arbitrary points that lie along edges, the first thing I think I should do is find a path from each of my arbitrary points to the nearest intersection. Okay, so I do that, and then once I've done that, I have two vertices, and I want a path between them. So I could use some graph traversal algorithm to find a path between my two intersections. Now, notice how it doesn't suggest DFS or BFS. You could use either of them. And this is a good time to bring up, there's a bias that I think we might have, which is if I were to ask, you have to choose one of them and give a justification, which one is better, then even I sort of feel like I might try BFS. Why would I want to use BFS? Because it seems to me BFS guarantees me that I follow the smallest number of edges, and that it seems like that means the shortest path, doesn't it? The answer actually is no, because there's no guarantee that a particular edge covers any particular amount of distance. That is, here is an edge that covers a small amount of distance. Here is an edge that covers a large amount of distance. And so while BFS is guaranteed to give us the smallest number of edges, and yes, frankly, if I were to implement the pathfinding problem with a roadmap using only a basic traversal like DFS or BFS, I would use BFS because the smaller number of edges does seem to maybe sometimes correlate to a shorter path. And generally, we want driving directions that are fast, that are the shortest possible path. There is no guarantee that if I use BFS, that the path that requires the smallest number of edges actually is the shortest total distance. And I can give an example of how that might work. Suppose I want to get from vertex A to, or location A to location B. All right, and that there is a road from location A to this vertex and then down to vertex B. All right, now suppose that from location A, there's also a winding country road that goes all the way around everything and then back to location B. This is just one edge though. It's one incredibly long edge. It could be like 100 kilometers long, and these two edges are like 40 meters in length each. If I were to run a BFS traversal starting at location A and ask for a path to location B, that BFS traversal is guaranteed to follow this huge long edge because BFS is guaranteed to find you the path with the smallest number of edges. Okay, so that would give me a 100 kilometer long traversal to get all the way to location B, which I can see from location A. Now, if I were to use DFS, I'm not guaranteed a better result. So if I start DFS at location A, well, either it for some reason starts by moving along the long edge, in which case it gets the same path as BFS, or it starts running in this direction. And we know the way DFS works, once it starts in a direction, it just keeps going. So DFS could give me a better path. Geographically. but it might not. But BFS, in this example, this contrived example, is guaranteed to give me the worst possible path, because BFS it works in terms of number of edges, the shortest path in terms of number of edges, not the shortest path in terms of some more complicated quality parameter. That is, the number of edges I follow in my driving path doesn't really correlate generally to the length of the path. There are other factors involved. Now, we may actually want to find the geographically shortest path between 2 points in a graph, and we can do that, but we don't have enough to do it yet. We're going to cover algorithms for that. That is a type of optimization algorithm in a while. I don't know, 7 or 8 lectures or something. So keep that in mind, that DFS and BFS as fundamental traversals are only able to understand the sort of topology of the graph. They can't understand underlying qualitative features of the graph, like if I decide that this particular edge is no good and I don't want to follow it, or I want to avoid following it if at all possible. If there are certain details about paths that give them higher or lower quality than others, and I want to encode those in, I need something more advanced than DFS or BFS. A standard example of that, again, is a shortest distance path, but there are other types of paths I could prioritize. I could, for example, want a path that has the fewest uphill segments as possible, that tries to stay on flat land as much as possible. And I could there's a class of algorithms that I can use to solve pathfinding problems like this that we're going to cover later on. Okay, what about this? So this is a sliding tile puzzle. This particular one, I guess we can call this 16 puzzle. And you can get these things and you can hold them in your hand. And it consists of this set of numbered tiles with one empty space. And you are allowed to move tiles into the empty space. So if I wanted, I could slide the tile labeled 3 down into the empty space. And that would mean the empty space is now up here. Or I could move the tile labeled 6 to the right into the empty space. So suppose I give you one of these puzzles that's been scrambled up like this. So the tiles are in some apparently arbitrary order. And my question is, can you find a sequence of valid moves? So for example, you move the 6 over here, then you move the 13 down, and then you move the 2 down. Some sequence of valid moves that produces this configuration, this solved state, where all the tiles are in numerical order, so top to bottom, left to right, and the empty space is at the bottom corner. So this is a puzzle, and so therefore a bit of a contrived problem, but I want to demonstrate that this is actually a pretty characteristic graph traversal problem, because we can model this problem in terms of where I am now. So I am standing on this state of the game, and if I were to move the 6 over, I am on a different state of the game. So I know where I am now, and with very local information, local knowledge about my surroundings, I can figure out where I can get within one move of where I am now. And so with that local information, I am actually modeling a set of pairwise relationships. And if I can model pairwise relationships, and I can keep doing that for every possible state, then I could use a graph traversal algorithm to find a path in this graph. So this is the 16 puzzle. For my next diagram, I'm going to scale back to the 9 puzzle, which has fewer rows and columns, just because the diagram is a bit complicated. So let's consider the 9 puzzle. Let's consider a particular board of the 9 puzzle, like this one here. What I could do is I could model using a graph. Now again, whether I store this graph in memory or not is a separate question, but I could think of this graph model existing where every state of the board, every possible arrangement of tiles is one vertex. And I connect 2 vertices together if I can get from one vertex to another in one valid move. So notice how if I start at this board here and I move the 2 up by 1, I get to this board here. So it makes sense because I was able to reach this state from this state in one valid move that I connect them by an edge. Also, I've chosen to use undirected edges here because moves are reversible. If I move the 2 back down, then I end up back at this board. So moves can go in either direction. If I notice that this was a type of game where the direction of a move made a difference, that is, moves were not always reversible, then I would probably want to use a directed graph. So if I do this, if I perform this modeling where for each particular board, it's easy for me to figure out which boards I can reach within one move. I just try every possible move available at that location. If I do that, I could model the entire set of states of the game as this graph. And so I build a board with all the possible states as vertices. I build a graph with all possible states of my board as vertices. And then if I want to find a sequence of moves, for example, starting here, that brings me to my goal state, I just use a traversal algorithm to find a path to the goal state. Now here it doesn't say whether I want to use DFS or BFS, although here I probably would use BFS because each edge that I follow is one total move. So there's no, unlike before where the distance of an edge in the pathfinding problem could be anything, like there's no way of knowing. Here, each edge is one move. And I assume with solving puzzles like this that I would like to use the fewest total number of moves if at all possible. So BFS guarantees me that the path I end up with requires the smallest total number of moves. Once I have a path to the goal states, once I find a path from my starting point, if I want to know the specific sequence of moves to make, I just look at each edge and I look at which move it encodes. So I can observe that this edge here is the move where I take the 2 and push it upwards. And then this edge here is the move where I take the 5 and push it upwards. And then finally, this edge here is the move where I take the 8 and I move it over to the left. I could, once I have my path, I could then read the path backwards, I guess, from the goal state to figure out which moves I have to make to get where I want to go. And so I can solve this problem. I can actually solve my sliding tile puzzle using graph traversals. Okay, here's an interesting one. This is actually an interdisciplinary application, the kind of thing where a computer scientist or software engineer would work to create some structure that could then be exploited by maybe geoscientists or ocean scientists. What I have here is a relatively low resolution, although not low enough to see everything at this scale, a low resolution grid covering the surface of the Earth. So suppose that we take a rectangular projection of the surface of the Earth, because the Earth, of course, is not a rectangle, and therefore we have to stretch it a bit to make it fit into a rectangular shape. And I have this 2D array of essentially integer values covering the surface of the Earth. I'll zoom in a little bit there. So if we look at the contents of this grid, either a particular cell, so again, these cells here aren't really rectangular areas of land, but for the sake of this being simple to describe, let's suppose this is a rectangular area of the Earth's surface. It's sort of a deformed rectangle because the Earth is a spheroid. Each of the elements of my 2D array, each of the elements of my grid, is either going to be a number indicating that the cell is water, that is, in this particular little parcel of Earth, it's just covered by ocean, or if it's a land cell, if it's an area that's predominantly land, it consists of a cardinal or ordinal, one of the 8 core directions, so north, northeast, east, southeast, whatever, going all the way around the compass. And the direction tells us if water is on this parcel of land, which direction does it flow? So if rain falls or if water ends up flowing into this piece of land from uphill, where does it go? In this case, it flows more or less south. And of course, there's some aggregation necessary here. In the gathering of scientific data, you always have that problem where you have to put up with a certain amount of inaccuracy because of the accuracy of your measurements. But fundamentally, if you look at any piece of land and you consider water that ends up on that land, so again, rain falling or water that flows in from uphill, then that land drains in some direction. And the direction is usually, broadly speaking, downhill. And so these could actually be generated. The direction in which water flows might be generated, although it's not really any of our business. We're not the geoscientists. This might be generated by evaluating topography data over the surface of the Earth and figuring out which direction is downhill with respect to each of these little cells of land. So what I have here is very local information. If I look at a single parcel of land, all I know is that in this parcel of land here, when rain falls on this or water flows into it, the water tends to flow. The downhill direction is approximately northwest. That's all I know. Local information about individual parcels of land. Suppose I give you one of these grids that shows this direction for all of the land cells on Earth. And I ask, I want you to take this local information and give me something, a very global structural model of the world's rivers. And it turns out that we can do this. Now, there are some aspects of the computation that we need domain-specific expertise for. So what we can definitely do ourselves is work out a model of where water flows by tracing. So if we look at this cell here, notice how this cell flows into the ocean. And we could argue that means this is essentially the mouth of a river. Maybe it's an incredibly small river, maybe it's an incredibly big one. But any cell that flows directly into the ocean sort of functions sort of like the mouth of a river. If we notice that tons and tons of water is flowing into this cell here, then it would make sense that there must be a physical river visible in this part of the Earth because there's so much water flowing through it. And it turns out this is actually the mouth of the Amazon River. So I would argue that that is probably fairly visible on the surface of the Earth. If we work backwards backwards from the mouth of a river. So if we were to look at the cells that flow into this cell here, we could also work out how the river looks upstream. In fact, we could trace all the way backwards to identify the entire drainage basin of the river. And that's what's happened here. Notice that this also contains, now my drawing is not going to be very good on this because there's so many colors, but notice how this also contains some indication of the thickness of the river, or thickness isn't the right word for that, the volume of water, the width of the river, the amount of water flowing through it. That's because there is research in, I guess, the earth and ocean science community or the geoscience community about this. This is not something about which I am an expert, but there is research that has suggested that there are ways of approximating the amount of water flowing through a particular area of land by knowing how much water is coming in from upstream. And that seems reasonable that they would have such research. And so this is the kind of thing where if you are collaborating with scientists, like geoscientists, they would provide that mathematical expertise and you would provide the structure to actually produce this modeling. And it turns out this model of, let's say, this is the Amazon River Basin, can be produced using the data on the previous slide via graph traversal algorithms. And what's interesting about this is if you look at the entire map, so if you look, for example, at North America, what you'll notice is I've used colors to indicate this. We can actually divide up the continent into colored river basins, where we know that if any water falls in this green region here, it makes its way slowly, it drains into the Amazon River Basin. It ends up flowing through the mouth of the Amazon River out to sea. And for the most part on the surface of the earth, most areas of land do drain eventually into the ocean. There are a few unusual places where apparently water drains just to some random place in the interior. I know very little about that besides to say that that's sort of interesting special case. And so the way that we model this is we can model the set of directions using a graph. And then once we have that, it turns out that a river basin itself, the river functions sort of like a tree, where if we think of the mouth of the river as the root of the tree, we can then trace upstream to find all of the other tributaries to the river. And then we can use that to estimate the total volume of water that's flowing. So it's actually a strangely straightforward application of graph algorithms. And what was especially weird about this, a reason that I'm putting it in these slides today, is that I actually saw this problem long ago as a co-op student, and I saw it in a co-op term I was doing the semester after I first learned about DFS. I described that light bulb moment that I had one day while hearing about DFS. And when this problem was described to me, it was described to me by a geophysicist who was not an expert in graph algorithms, who, of course, viewed the calculation being done as pretty complicated and important, and was describing it to me in very light terms because that he was afraid that the description would bore me or I'd be intimidated by it. And of course I was. I mean, I did hear about it. It was like, how am I supposed to help with this? I know nothing about earth science. And when I got a chance to look at it, I did realize, as I'm sure you would in the same position, that the actual structure that was being desired was just the result of applying a traversal algorithm. And so at the time, DFS was my favorite algorithm, and I got to use it for this. And not only was that lots of fun, it also really impressed my supervisor because he had thought this was a peculiar domain-specific problem and was pretty impressed that, a computer scientist, no less, was able to find some way of interpreting this. So the idea is basically this. Let's consider a few cells. Suppose we've got this cell here which points east, and then its neighbor also points east, and below it we've got a cell that points north. All right, and then who knows what's happening over here. What I do is I model each cell as a vertex, and I connect each vertex to the cell it flows into. So if I look at these two here, I would connect these two, I would connect these two, and I would connect these two. And then suppose that this is the ocean. Or actually, no, let's do one more layer. So suppose we have the ocean here. Okay, so if I notice that there's a cell that flows directly into the ocean, then I can argue that must be the mouth of a river. So I'll start at this cell and I'll do a traversal working backwards, working sort of inland from the mouth of the river. And if I just, shade in all the cells that I reach, I will find every cell that drains into the mouth of the river, that actually drains into this river system. And so then I can tag all of these cells, all of these parts of the Earth's surface as being part of the river basin associated with this thing. If if I then also want to do things like estimate the total amount of water flowing through this river, what I could do is, if I had data available that told me how much total, let's say, precipitation is falling in each of the cells in the river basin, or how much water is found in those cells, I could use that to estimate the total amount of water that makes its way to the mouth of the river, through the ocean. And that would be how I'm able to estimate things like the sort of width of this river. This is, of course, a conceptual width. It doesn't actually take up this amount of, it's not this width on the Earth's actual surface, although the Amazon River is pretty huge. But there is, you can use, once you've isolated the sort of tree that corresponds to each river basin, you can then use analytics that apply to that entire basin by just traversing the entire tree. And so the way that the problem might be solved if we want to traverse all of the world's rivers is to simply create the graph, identify all of the vertices that flow directly into an ocean, those are the mouths of the rivers, and then perform some kind of traversal working upstream from there. It's tempting to use directed graphs for this. Like it makes sense to say, okay, these cells flow in this direction, so let's use a direction on the edges. You could do that, but because the traversal you want to do tends to be going upstream, it's often easier just to use undirected edges and just have the direction be implicit in what kind of operation you're doing, or you have to do a thing where you write a traversal that actually goes opposite the direction of edges, which is fine, but feels sort of wrong. It feels sort of weird. And then once you know what's in each river basin, you can just tag everything as being part of the same basin, and you can either never do a traversal again because you've already labeled which cells are part of which river basin, or you can do more traversals to estimate things like the total volume coming in from upstream at each point. But in any event, what we have here is this interdisciplinary application where bringing in some knowledge from computer science and math or software engineering allows us to find a very nice, rigorous mathematical model for this underlying natural scientific structure, where if you show this to geoscientists, they now have a much easier way of understanding how to compute this sort of structure, because they had been working with models like this, the idea of modeling the river as something that we know to be basically a tree, but didn't necessarily realize that this was a standard application of graph theory and graph algorithms. I have one more problem to solve, and this is definitely a very contrived exercise. This is one of those sort of thinking puzzle things, and I originally found it in that context as a sort of thinking puzzle. It involves buckets, and I guess I've talked a lot about buckets today. So you're given 3 buckets with capacities 7, 5, and 2, and they are unlabeled, but you do know their capacity. So if I say this bucket is full, you know that it contains exactly 7 units of water. If I were to fill it randomly halfway up, we have no way of knowing how much is in there unless we can reason about how I filled it. So you have buckets with capacity 7, 5, and 2. The largest one with capacity 7 is full. Your task is to find some way to measure exactly 4 units of water. When I say exactly, I mean you can't eyeball it. You can't just, let's say, fill up the bucket with 5 capacity and say, oh, that's more or less 80% full, therefore it's 4 units. No, you can't eyeball it. You have to somehow argue that what you have measured is exactly 4 units of water. And here are the rules of what you are allowed to do. You are allowed to pour water between buckets, but you can't add any new water to the system and you can't spill anything. Somehow these are completely spill-proof buckets. When you pour between 2 buckets, you must either pour until the bucket you started with is empty or the bucket you're pouring into is full. So in this case, if I were to pour from the bucket containing 7 into the bucket that can contain 5, I would have to fill the bucket containing 5 all the way up. And then I would be left with 2 units in the bucket containing 7. And I could use that. So I would be able to justify that at that point I have exactly 2 units in this bucket. So I'll show off the solution to this problem and we'll talk about a few other examples. So it turns out I can solve this in 4 pouring operations. I begin by pouring from the bucket with 7 into the bucket with 5. Now at this step, I have to have 2 units left in the bucket with 7 because I'm not allowed to overfill this bucket here. And I could argue that this is justifiably must be exactly 2 units because I didn't spill anything and I used exactly 5 units filling this one up. The goal of this puzzle is to arrive at a state where I've got what I know to be 4 units in any of the buckets, but it'll I think end up being in this bucket here. Okay, so I now have 5 units in bucket 2. I pour 2 of those units into bucket 3. And what maybe you can see at this point is, hey, if I combine these 2 units with these 2 units, I definitely have 4 units. And so I just pour from bucket 3 back into bucket 1, and now I've got 4 units. So the problem is solved when any of my buckets contains exactly the 4 units that I wanted. Okay, so there's the setup for my problem. Let's try it again with a different example. Starting from these buckets, find a sequence that also measures 4 units of water. Okay, this can be done, I think, also in 4 steps or with 4 different states. So there they are. And when I draw the states like this, with arrows between them, I can't help but be reminded that maybe this is with different states and operations I can perform. It seems like this might be something that fits very well into this lecture. We've already actually seen with the sliding tile puzzle a way of modeling different states using vertices and operations using edges. So I can solve this one in 4 steps as well. Eventually I end up with 4 units of water in the bucket with capacity 6. And of course the question I'm getting to here is, can we design an algorithm for this? Before I talk about that, first, I should observe that if I told you to solve this problem and then come back later and prove to me that you actually solved it, that is, I don't just want to see a bucket with 4 units, I want you to give me evidence that you followed the rules. You could do it by writing down each state you pass through, let's say as a triple, as 3 numbers. You start in the one with 6 units and 0 and 0, and you end in the one with 4 units and 2 and 0. And you could just write down each intermediate state just as the number of things in each bucket. And if you give me this readout, I could look at each pair of states and I could verify that the operation you did at each step followed the rules. That is, I could look at this operation here, this transition, and say, okay, you poured from this bucket into this one, and that's valid because you filled the bucket all the way up, and you had 1 unit left in the first bucket. Okay, so I could look at this readout and I could verify that you followed the rules at each step. Another thing to consider is, with these thinking puzzles, because of course the puzzle was originally designed as a sort of a logic problem for humans, maybe you look at it and say, yeah, you could just try, you could view this as a heuristic exercise and realize that in your head you can come up with a solution in a few steps. I want to emphasize that, yes, it turns out in this example I probably could solve this one on paper in a couple of minutes if I just fiddled around with it. But you can come up with examples of this that do take quite a long time. So this one here, where I give you these 3 buckets and ask you to measure 9 units, this requires at least 12 steps. And you can, after the lecture is over, consider how I'm able to know that there's no way of doing it in fewer than 12 steps, or with fewer than 12 different states. I guess there are 11 total pouring operations. So here they are. If I want to measure 9 units, there's my 9 units there, I have to follow this chain of operations. And this is the kind of thing where with this many steps, if you just sat down and tried it by trial and error and you got stuck halfway through, that could be a pretty painful process. So hopefully that's enough of a justification that we might want to come up with an algorithm to do this. And so the question is, can we design an algorithm that does this? Design an algorithm that takes some initial configuration of buckets, which doesn't actually have to be where one bucket is full and the others are empty. It just takes some initial configuration and then some goal measurement, for example, 6 units, and then outputs a sequence of pouring operations or a sequence of states that you pass through to obtain the measurement, if such a sequence exists, because perhaps it's the case that there is no way of forming a particular number of units given a particular set of buckets. So off the top of my head, I could imagine cases where maybe every bucket has an even capacity, and it sounds like if that happens, and it's probably impossible to measure an odd number of units of water. So there could be cases where you can't actually achieve your goal. As with the other algorithms that we've seen today, I want an algorithm that's either finds me a solution or is able to accurately tell me that no solution exists. That is, if it reports that there is no solution, it must be correct, of course. So I could model this, unsurprisingly, obviously, with a graph, and I'm going to apologize in advance that the graph I'm going to draw on these slides is a bit of a mess because there's so many different edges to play with here. So what I do is I use a vertex to represent each possible state of the buckets. So my start state, where the first bucket is full with 8 units, is this one here, and I guess I want a goal state where I find 6 units. And we notice, so the graph I've drawn here actually doesn't model literally every possible state. You notice that there actually is no vertex on this graph for the case where all 3 buckets are empty. Now, if you wrote an algorithm for this, you probably would do that. You would just generate a state for literally every possible set of fill levels of each bucket. Whether or not you ever actually reach those states is a different question. It's easier just to make a bunch of vertices you never use than to try and figure out which vertices you need in advance. For the sake of the diagram on these slides, I need all the help I can get, so I only added the vertices that actually are relevant to the solution. If the capacities of my buckets, in this case they're 8, 3, and 1, if the capacities are C1, C2, and C3, the number of vertices that I need is at most this, it's not actually, I think it might be this number, C1 plus 1 times C2 plus 2 times C3 plus 3. Or not C3 plus 3, what am I talking about? Sorry, each thing plus 1. And the reason it's plus 1 and not just C1 times C2 times C3 is that the bucket could be 100% full, but it could also be 100% 100% empty. There could actually be 0 things in it. So the number of total possible levels of each bucket is actually the capacity plus 1, not just the capacity itself. In any event, though, the number of vertices I need is going to be some multiple, more or less, of the capacities. So the reason that's important is just so that I know I'm not going to create some infinite number of vertices or anything. If the capacities are all integers, there are a discrete number of different levels each bucket can be at, and therefore a discrete number of combinations of those levels of buckets. However, it's easy to identify, because I'm not allowed to spill any water, it's easy to identify that certain states can never be reached. For example, there will never be a situation where the first bucket in this example contains less than 4 units, because here's the case where it contains 4 units. The other 2 buckets are full. There's nowhere for the other units of water to go. I have no way of storing less than 4 units in the first bucket because I have nowhere to put them, basically. But I could still create vertices for those cases. That is, I could create a vertex for the case where I have 3 out of 8, and then 3 out of 3, and 1 out of 1, even though that doesn't have the right amount of water and therefore wouldn't be relevant to my solution. I could still create a vertex for that for the sake of having easy to write code, I guess. So the capacities here are 8, 3, and 1. I don't know why we needed an extra slide to demonstrate that. And so then I add edges corresponding to valid pouring operations. Let's look at this edge here between these 2 states. So in this case, what I could do is I could take the 1 unit in bucket number 2 and I could pour it into bucket number 1. And so now bucket number 1 had 6 units, but now it has 7 units. But notice that that pouring operation isn't reversible. There's no way of pouring exactly 1 unit into this bucket with 3 units capacity. And so that tells me that the pouring operations aren't reversible, and therefore that edges, if I'm defining an edge to correspond to a valid pouring operation, edges need to be directed edges, because I can't necessarily go back once I've followed an edge. And so there are some pouring operations that are reversible. So I guess these ones here, let's see. Yeah, these ones here are reversible because I can pour from the bucket containing 1 into the bucket containing 3 and back again. And so this is a bidirectional, or it's actually 2 directed edges that I've drawn. I mean, that is, formally it's these 2 edges, but I've drawn them as one to clean up the messy diagram. So edges correspond to the pouring operation, and I need to use directed edges because a pouring operation may not be reversible. So that means I'm now using a directed graph, and as usual, once you have a directed graph, you should assume all of your operations need to respect edge directions, because why did you make the decision to have directed edges unless the directions mean something? Okay, so I can construct the graph itself with very local knowledge. All I do is look at the state of my system. Let's go find the diagram of buckets. There it is. So I look at this state here, and I just try all possible pouring operations. And then once I'm done that, I have a list of all the states I can reach from my current location, which means I can build the graph with local knowledge of each state. It's relatively straightforward if I'm at a particular state U to compute all of the other states W that I can reach from my current position. And this is great. This is exactly the benefit I want using graphs. I want to go from a collection of local information, that is local knowledge about every vertex that I'm standing on, and then use a graph traversal algorithm to get some global property. For example, a path, which is what I'm going to end up wanting, from my start position to the goal, to actually measuring 6 units of water somewhere. Okay, so after I construct the graph, suppose I use a DFS traversal. If I use a DFS traversal and I locate some state with 6 units, where any of the 3 buckets contains 6 units, in this case it has to be the first bucket, and I use DFS to find a path, and then I read off that path, I now have a sequence of pouring operations that gets me from my initial state to a state where I've measured 6 units. And you could say, why did you use DFS for this? And the answer is, well, because frankly, BFS is probably a better choice here, and I wanted to give DFS a little bit of time to shine anyway. So DFS gives me a path of, I guess, 6 vertices, a path of length 5. If I were to use BFS, of course, BFS guarantees the shortest possible path in terms of the number of edges. But here, as in the sliding tile puzzle, each edge corresponds to exactly 1 pouring operation. So that means if I want to minimize pouring operations, I do want to minimize the number of edges. So it does make sense here that I would pretty much always want to use BFS for this. So using BFS, I managed to get a path of length 3. I pass through a total of 4 states, including the start state. I start with 8 in my first bucket. I then pour into my second bucket, and then I pour from the second bucket into the third bucket, and then I finally am able to get 6 units by pouring from the third bucket back into the first bucket. Okay, so this is obviously a contrived problem, but I hope that over the course of this lecture I was able to demonstrate that a lot of problems, it's hiding surprisingly close to the surface, that the problem itself can be modeled and solved using graph algorithms. As long as you can find a way of turning it into a graph, you can then take a standard algorithm down off the shelf. Notice that basically at no point during this lecture did we really modify DFS or BFS. The closest we came was in the discussion of bipartitions, observing that as we visit a vertex, we can color it to be the opposite color of its parent. Nothing about the traversal logic was really changed. I just took the algorithm down off the shelf, and it came with its own proof of correctness and its own results about its efficiency, and I just plugged it in. The trick was finding a way of modeling the problem using a graph, and it is surprising how many problems can turn into graphs if you know where to look. And over time, you're going to develop that instinct as well, of looking at a new problem and saying, does this look like a collection of different states that I can move between by some easy to understand operation? If so, then it looks like I might have a graph on my hands. And we're going to see that applied to a more advanced problem in the next couple of lectures. So we're going to start talking about more advanced graph algorithms, ways of modifying DFS and BFS for specific cases. And notice that in those cases, usually our goal is just to find some way of viewing our problem a certain way through the lens of graph theory so that we can find an excuse to employ our traversal algorithms on it.